Test. So people online, can you hear me? All right, thank you. Okay, good evening. Let's get started. I understand there's an exam tonight. So you can expect that all students will show up today. Anyway, okay, so let's continue on the lecture 248. In the previous lecture, we finished the topic on directional derivative. Basically, the formula for calculating directional derivative is listed here. Okay, as a quick review, so what this gives us is, right, it's basically give us a rate of change in function f when there is a change in the direction of u hat. The calculation is very straightforward. So all you need to do is to calculate the gradient of the function f, then dot product with the direction given by the unit vector u hat, right? Then you get the so-called directional derivative. So in this lecture here, we're going to cover two different things. First of all, we're going to go back to the concept estimating change. I missed the E here. Estimate the change. And then we'll get on another topic called to look at the mean and the max of a function of two variables. Okay. So let's take a look at the first one here. And that is, how do we estimate changes? So this topic we actually had covered already. You know, I remember when we covered total differential, we have a formula how to estimate the changes. So now we're getting back to the same topic. Now this time we're going to use this directional derivative concept to derive a different formula, which is actually more general formula, okay, in terms of estimating the changes. So here's the formulation in the problem. Given a function, two variables, and then assuming that initially at P naught, X naught, Y naught location. All right, so basically, graphically, it looks like this. So here you have a surface, And then this is your initial location. At the initial location, you are at this z naught, right, equal to f of x naught y naught. So you're here. So now, okay, let's say we move from the initial location, okay, to, let's call it the final location. And move it to final location P1. How do we move it? So basically we change the x naught by delta x, change the y naught by delta y. All right, so delta x, delta y, just fairly general notation, a small change within the range, right, within this scope, within the area of x naught, y naught. So technically, it could be anywhere. So it could be going from here to here, right? That could be your P1. Okay. So it's a little bit too much, but anyway, so you could be moving to this way, right? Could be any directions. And once you move to the P1 location, then apparently at the P1, the corresponding location on the surface, right? Let's call it Z1. Then what we try to find, the objective try to find is, right? What is the difference between the Z1 and Z0? And how do we estimate that difference? Okay, so basically there's a delta F, right, equal to Z1 minus Z0. How do we estimate that? Okay, approximately equal to what? Okay, so that's the idea. So let's see how we can deal with this. Right, so ultimately we want to derive a formula for estimating these changes. Okay, when you're moving from P0 to P1. So a different way of saying this is, when you move from P0 to P1, you could denote, right, this is a direction of U hat. So the next question you can say, okay, so then what determines the direction U hat then? Right, what determines the direction U hat? The delta x, delta y, right? So you change, you move a little bit delta x this way, move a little bit delta y that way, then you have this U hat determined. Okay. So how you're moving in the x naught direction or y naught direction, right, determines finally the U hat direction. So alternatively, basically, to see the question is, if I move in the U hat direction, then what would be the approximate change in the function f? Okay, so that's alternative seeing this. Okay, so let's formally derive this, but before formally derive this, recall, okay? Recall what we did, okay, in the previous lectures. So recall this total differential. So total differential formula is df equal to fx dx plus fy dy. Okay, and then from here we have this delta f is approximately fx delta x plus fy delta y. Okay, yeah. So this is actually what we used, right, in the previous lecture, how we estimate the change. That works actually perfectly for this question, because if you know delta x, you know delta y, then you can just plug in here, and you also know the P0, then you'll be able to calculate, or you will be able to estimate the change delta F. Okay, so that's perfect, okay? But I wanted to have a more general formula. Okay, more general formula is now instead of giving me a delta x, delta y, how about I see things differently? So how about what is this delta f? Okay, what is the delta f if we move in u hat direction by a displacement of delta s? Okay, so let's say it differently, right? Same question, same scenario, right? Same scenario. Instead of saying you are moving from x naught y naught to x naught plus delta x, y naught plus delta y. Okay. So now we're saying we're moving in this direction and moved by a delta s amount of a displacement. Then how can we calculate this approximate change in the function f? Okay. So that's the second part of the question, right? So this is the part of the question we want to find a formula here. So here's what we can do. I'm gonna work based on the previous question, okay? Work based on the information given at it here, okay? And see we'll derive a formula here. All right, so from P naught to P1, right? So from P naught to P1, so what happened here, right? What exactly is going on? So from P naught to P1, right? Technically, I can see it is moving, okay, in U hat by delta S. So the question is, what is U hat? What is the delta S? So we're going to derive two expressions for the U hat and the delta S. Okay. Yeah. So let's try it. So what's U hat? U hat is basically a direction given by the vector P naught P1, right? So I can certainly create a vector based on P naught P1 and then normalize it. I'll get the U hat. So let's do that. Let's try the U hat to find a U hat here. And so what is P naught P1 first? You use the coordinate P1 minus the coordinates of P naught. So you get delta X, delta Y. So the U hat is basically normalized P naught P1. And that'll give you the delta X, delta Y vector divided by its magnitude. Okay. That's U hat. Okay. So once we get this, okay, let's look at what is the and what is delta S? Okay. So delta S is basically the absolute value of P naught P1, right? That's how much it moved from here to here. So then what's delta S? So delta S is basically delta X squared plus delta Y squared. Okay. Yeah. Good. So now I got U hat, I got the delta S. Okay. I'm gonna go back to my initial review at here, okay, that formula for the directional derivative. Okay. So formula for direction derivative. The dd formula is df over ds in the direction of u hat equal to del f dot u hat. Okay, that's your directional derivative formula. Okay. And from this formula, I'll manipulate this very simply. So you got a df over ds set here. So I'm going to multiply the ds to the right side. Okay. So then you get df equal del f dot u hat times ds, right? Times ds. Okay. So this is a differential. So that's why you got an equal sign added here, right? Now what if I change the d to delta? Then you have an approximation sign, delta f equal to this one. So then you get gradient dot u hat times delta s. So all the straight d differential is changed to delta sign. So the equal sign is changed to approximation. So now you can see the u hat delta s shows up right here. So if I substitute what I have derived into this formula added here, right? If I substitute basically the u hat over here, the delta s over here. So let's see what we get. So what do we have for u hat? It's that delta x, delta y over delta x squared plus delta y squared. Okay, and bracket times delta s. You get this. And apparently, you can cancel this out. And then you have delta f, not delta, del f dot delta f, delta x, delta y. Right. So basically, at the end, your approximate change is approximately equal to the gradient dot delta x, delta y. And look at that. That's what? That's exactly the same results as your from the total differential approximation formula, right? This is basically the same formula. Okay. So all I'm doing here is I'm showing there is an alternative way to calculate the approximate change. And that alternative way is this one. So we don't have to rely on the total differential formula to approximate a change. We could use this formula, which is from the directional derivative, to do estimated change calculation. So if you look at this formula here, delta x, delta y is not involved, right? What's involved is the direction. What's involved is also a displacement in that direction. Okay. So this is the formula that we will use, okay, to calculate this approximate change. So I'll give you an example here, okay? So let's say we have a function of two variables added here. So y sine s plus 2yz. And then initial point is 0, y, 0. Moving to final location 2, 2, negative 2. In So moving from here to here by how much? By 0.1 unit. So it basically you're moving from here in the direction. Okay. So this gives us a direction of moving. Okay, so that's the direction of a change. You change 0.1 units given by this direction. That's basically the given condition in here. Okay. And then we want to estimate, okay, how much change in the function f, okay, given the conditions at here. So how do we do? Let's use the formula, exactly use the formula, this formula here to do estimated change. Okay. So that formula asks us to calculate grading. Okay, we need the grading vector, and we also not only the gradient, just we need the grading vector at initial location. Okay, 0, 1, 0. So basically, now this is a function of now this one here. That's sorry. This is a function of 3 variables. Okay, so we can extend the formula to basically to any arbitrary variables. So you get fx, fy, and fz. Then calculate this gradient at p0 location. Okay. Calculate the partial derivative first. Partial f partial x is y cosine x. Partial f partial y. You got 2 y terms here, so sine x plus 2z. Partial f partial z, 2y. Then plugging 0, 1, 0. Okay. So y is 1, x is 0, okay, and z is 0. So I think you got 1, 0, 2. Okay, second term is 0. Okay, that's the gradient at p0 location for the function f. So once we get this, then we need to calculate. You look at the formula. What else do we need? We also need the u hat, the unit vector representing the direction of a change. So how do we get that? Okay, so we got the direction. We got the vector pointing to the direction. The vector is p not p1, right? Yeah. So the u hat equal to p not p1, and then normalize it. P not P1, use a 2 minus 0, 2 minus 1, negative 2 minus 0, so 2, 1, negative 2. And divided by its magnitude, so 2, 4, 5, 4, so 9, root, so it's 3, right? Yeah. So 1/3, 2, 1, negative 2. So finally, you putting things together. So you also have delta S given 0.1 unit. Okay. So then my delta F is approximately using the gradient calculated dot U hat multiplied by delta S. So I get 102 dot 1/3 to 1 negative 2 times 0.1. Okay, so when you calculate out everything, you get negative 2/3 times 0.1. So that's approximately negative 0.067 unit. Basically, the function has an approximate change of this much, okay, based on the current given conditions. So far, right, the objective is to obtain a generalized formula for estimating change in the function. Okay. And that formula is this one here. And this formula, certainly, as you can see, as we proved, okay, it contains that formula for estimating change when we learn the total differential. So in the future, if there's a question of estimating change, the first thing jumps in mind should be this formula now. Okay? All you need to do is to fitting all the puzzles right into the formula here. What is the direction of change? How much you're changing in a direction? And what's the gradient at the location? And then you calculate to use the formula. Okay, that's basically the concept of estimating change. Okay. Any questions on this topic? It's more or less related to directional derivative, right? It's basically derived from directional derivative. Question: can U hat be a vector parallel, or does it have to be P not P1? It doesn't have to be, right? U hat certainly can be any vectors parallel, but in this question, this is the information the only information you can use to find a U hat vector, and the U hat has to be a unit vector because there's no other information you can derive a U hat for this example. U hat is a unit vector, don't forget that. Okay. All right, so now that's sort of a wrap up this directional derivative concept plus the previous gradient vector concept. Right. And in the next couple lectures, again, we're gonna shy away from the vector a little bit. Okay. Well, actually, we're not really completely going away from vector. We're gonna talk a little bit about the optimization concept. And after that, and then we'll go back to the vector field. We'll do multivariable. We'll do multiple integrals, okay, with multiple variable functions. So the first optimization problem we can talk about is basically it's a min and max problem. Sometimes we call it also called unconstrained problem. And after unconstrained problem, then we'll talk about constrained problem. Okay. So basically, I will have two big part of the topic here to cover. Okay. Unconstrained and constrained. So let's look at the first part, unconstrained problem. Before we formally introduce this unconstrained problem, I need to cover a little bit the concepts, okay, that related to this unconstrained problem. Okay, so some concept. So first concept. Extreme values. Extreme values. So I'll using graphical to illustrate what's extreme values, right? This is much easier. I'll use a surface. So use a let's use a surface. Consider an arbitrary surface, because that's what we can graph, right, in 3D space. So let's consider even a little bit more complicated surface. Okay, so let's say you have a mountain up and downs, right? And there's top, okay, and there's trough, right? So all of these locations, right? All of the locations that you can see here, the locations over here, here, and here. Okay. So they are the so-called extreme values, and even here, right? Extreme values. So all of these are extreme. It sort of explains itself. Why extreme? I mean, you basically reached a top over here and reach the bottom here. You reach another top, you reach another bottom, right? Yeah. The wording is essentially sort of just explain itself what really is stream here. Okay. However, we need to be a little more specific, right? Meaning, for example, you see, if you see this is the top, and you see this is the top, so then which one is the top then, right? There's got to be a one that's actually the top, okay? But this is the top, because if you only look at this area, and that is also top, and you look at this area, that's the top, and you look at this area, that's the bottom, and you look at this area, obviously this one is lower than this one here, right? So the bottom line is, okay, we have the so-called local minimum or local maximum. Okay. So differentiates this all the extreme values. Okay, so I see, so all of them are extreme values. However, right, some of them, I mean, not some of them, all of them are local, can be called, all of them can be called local minimum or local maximum, right? Because if you look at this one here, certainly it's a local minimum. You can look at this one here, yes, it is also local minimum relative to this area, right? Yeah. And then you can also claim that the two locations here, okay, let's say you restrict yourself to this part of the mountain. So these two locations, A and B. So this A and B, so they're called boundary values. Okay. Right, that's the boundary values. I mean, if you have nowhere else to care about, I mean, the boundary value could be a local mean or local max too, right? Yeah. But however, okay, in your mind, and you certainly will be more interested in what is the global mean and max. Right? So you can see, okay, so then where is the actual bottom and where is the actual maximum, a top, right, of the whole mountain area. Okay? So that's something you also be interested is, so that part is described by the so-called global mean and maximum, right? Yeah. So for this portion of the lecture, okay, so we call this is unconstrained problem, is that we will try to find, okay, we'll try to find all of these local critical, so-called critical point or extreme values. So the objective is to find all the extreme values. If we can find all the extreme values, then we can actually find the global mean and global max, basically. Okay, yeah. So that's the objective. Okay. Now, I want to jog your mind and basically to connect some dots, okay, before we look at the actual the actual formulas or theories of how to find those local means and local max here, right? Yeah. So if you recall, for function of a single variable, okay, so when you have a function single variable, can you tell me how do you find the location of so-called critical point? Yes. What's the first step? Let's see what's the first step. Anybody? What's the first step? Go ahead. Yeah. Derivative equal to 0. Is that what you said? Yes. Right. The first step is you set derivative to be 0. So you basically you set f prime equal to 0. Okay. And what's the second step? And then that's what one of the students, I don't remember who said that. Is that you said that? Yeah. Then that's what the other student said. You look at the sign of your second order derivative, right? And depending on the sign of the second order derivative, then you can claim whether that location is a minimum location or is it a maximum location. Okay. Now, however, if you recall that, aside from the minimum location and maximum location, there is one also special situation, right? Do you remember that? What's the what's a third situation aside from minimum, maximum? Yes. Saddle point is a point referred to 3D case. In 1D, what's the point? It's called inflection point, right? Inflection. Yeah. So there's a situation. So you can get a minimum, you can get a maximum, or there's an inflection location, okay, or point. Okay. Now that's function of single variables. Okay. So we can make an analogy at it here regarding the function of two variables, and then we can compare with the results of function of single variables. Okay. Yeah. All right. So now let's consider function of two variables now. So the first question is, if function single variable, you can get those so-called extreme values by setting the derivative equal to 0. Then take a wild guess. What should I do for function of a function of two variables? Gradient equal to what? 0, exactly. Right? So this is basically our theory number 1. Okay. And theory number 1 is very straightforward theory. So remember when we learned the greetings, and I have emphasized the meaning of the greeting vector. And I said the first meaning or the first comment, the first statement about greeting vector is that it points to the direction of the greatest increase in the function f, right? So if it points to the direction of the greatest increase function f, then when function f reach either the top or the bottom like this at here, then there's no direction to point to. That means that directional derivative, that means that gradient, right, will be 0. Okay, so the gradient equal to 0 is basically the first order derivative equal to 0 at here. And that's the first theory number 1. We called it a derivative test. And this test is supposed to give me all the local extreme values or local extreme locations. Right? And this procedure is to set the gradient equal to 0. And setting gradient equal to 0 for function two variables basically means you get two equations. You're letting the two partial derivatives equal to 0 because you're setting the vector to be 0. And that, right, whatever that the two equations maybe will give you certain solutions, right, for x and y. And the x, y together indicate the location. Okay. And if there's situation like this one here, then you will get like 4 different locations, right, or 4 solutions at here. for a set of solutions. Okay. So that's the idea, right? Same idea as a function single variable. And of course, the calculation will be a little more complicated. Okay. So now if I assume, let's assume this A and B is the solution. Okay. So if I assume this A and B is a solution, we call AB, we call this AB critical point. Or extreme location. So they're all the same meaning in here. However, there is also there is the special case, right? Just like the special case for the function single variables. For function of two variables, right? Aside from this extreme location, so basically you have, so A, B here could be a mean, a max, or as what the student just, or a saddle point. So the saddle point, I think I explained it to you in when we graph the function of the saddle, right? Saddle point basically means at that location, you go one way, it goes up, you go the other way, it goes down. So it's neither a minimum location nor a maximum location, right? Just like an inflection point, you go this way for function single variables, right? You go this way, it goes down, you go the other way, it goes up, right? Function of inflection point, an example of inflection point, if you have x cube function, right? It's more or less like this. So you have a basically inflection point over here. Okay. The first order derivative zero is zero here, but it's neither a minimum nor it's a maximum. So same thing, right? So when you do the first derivative test, you could end up with the scenarios like this. But all of this, right, doesn't matter what situation you end up with, they can also be called critical points, right? So now the next question here, how am I able to determine what exactly that location is, right? So we need that exactly like for function of single variables. To determine that, we do a second order derivative verification. So for function of two variables, we also have the so-called second derivative test. And we can use this second derivative test to identify the actual type of location, okay, for the critical points. So let me write down this second derivative test. It's a little bit long, and you don't have to worry about to memorize the whole thing. You will have the formula for the final exam, but I'm going to write it down at here. Okay. So there are three conditions to check. Okay. To check what actually four conditions. Yeah, four. Okay. Number one. Sorry. Before we write down here, let's assume certain conditions. So let's assume that this AB give us a critical point. Basically means AB is a solution of the first order derivative test. Then that means if you substitute AB location into the partial derivative partial x, it should be 0. If you substitute into that, you should also get a 0. Okay. Then, and let's look at all the detailed conditions. First condition, function f has a local maximum at AB. Okay. If the following conditions are satisfied. First condition is fxx less than 0 and fxx fyy minus fxy squared greater than 0 at AB. That's the first statement. So as you can see, you need to check whether this is less than 0 or this is greater than 0. They have to be satisfied at the same time in order to claim that this AB is a local maximum. Okay, yeah. Okay, so that deals with the local maximum. The second one is a local minimum at AB. And if the following condition is satisfied, so fxx is more than 0 and fxx fyy minus fxy greater than 0 at AB. That's the second condition. So if you compare the second statement, the difference between the second one and the first one is, right, that what's changed is just the first one, the fx from negative to positive. As a matter of fact, function single variables, if fx is less than 0, is it a min or max? Huh? Is it min or max? Give you a min or max? Max, right? If fx less than greater than 0, it give you a mean location, right? And that's very much the same as the conditions given here, right? Second order derivative. Okay, yeah. So third statement, okay, third statement, they actually deal with the saddle situation now. Okay. So function f has a saddle point at AB. If the fx fyy minus fxy squared less than 0 at the AB location. Yeah. So this term is less than 0. And the previously two condition, that term is more than 0. Okay. So that gives you the saddle. And then the last situation is, okay, this second order derivative test is inconclusive if it turns out that this term is equal to 0 at AB. That's a fourth condition. Now you might wonder, then what happens if it's inconclusive? And then what should we do? So what you should do is you do there's a third order derivative test. So but that's out of the scope of this class. Okay, yeah. So everything that I listed it here. So I'm not gonna give you a proof. Actually, I will provide you a supplemental document. Okay, I'll put it in the Canvas as a proof how each one of them played out. Okay, to be either local mean or local max or saddle point. And the bottom tools, the fundamental tools that we use to show the proof is basically Taylor series expansion for multivariable functions. Okay. And as a matter of fact, you can clearly see that term, right? Is kind of important in all of the four statements. So this term is a result of the determinant calculation of this 2 by 2 matrix. So if you calculate the determinant of this, and you get fx fyy minus fxy squared, right? Yeah. So this matrix, for your interest, is called Hertzing matrix. So in mathematics, there are few metrics. There are few metrics that are very important. And there's one you probably already dealing with called Jacobian matrix. So we actually will also use that, okay, very shortly in the next couple of weeks of a lecture using Jacobian matrix. And then the next order from Jacobian matrix, then you get this Hertzing matrix. So this is also a very important matrix. As you can see, this is one place you use this Hertzing. Sometimes we just write it as the D. Let me see, there's a student, I see, yeah, fyx, yes. But fxy or fyx, if we're dealing with nice functions, right, they're basically the same. So that's why you can get fxy squared. Okay, good point. It's a question from online. Okay. So I don't have time to give you an example on how to use this criteria here to check the type of locations, critical locations. We'll look at that in the next lecture. Okay? But we'll strictly follow basically the conditions here, right, to test the critical locations. Okay. All right, so I'll see you guys shortly online. If you can join maybe at least half an hour, sorry, the half an hour too much, 15 minutes, 10 to 15 minutes before the final exam, the midterm starts. I appreciate that. Okay. Yeah. So we'll see you on the Zoom link shortly. Okay. Any questions? Feel free to come over.